spectroscopy. I would do a cartwheel in the grass, but this makes me nervous. I look at that. I busted my watch one time because my wrist expanded and my watch busted. He goes, "That could have been your wrist." Oh. No, my wrist is stronger than my watch. Oh, yeah. And so what we're talking about is rotational spectroscopy today. Now, I want to say from the beginning, this is less applicable to your lives than the next lecture, but we need to talk about this first. So we need to talk about rotational spectroscopy because next time we're going to talk about row vibrational. So we're going to add rotation to the vibrations. So you can see why we need to talk about rotations first. So we're going to talk about rotations today, and then we'll get into the combination of rotations and vibrations. So the main thing you want to talk about with rotation of a molecule is this B here. That's the rotational constant. And it's sort of it's the energy difference between the energy levels. Okay, so we've already seen this kind of in our particle in a box thing when we pulled out the front pieces and we had the quantum numbers difference like n plus 1 minus n squared and all of that. The thing that came out front was h squared over 8ml squared. We saw that. And so the ml squared part was in the denominator. And here's the rotational constant. And in the bottom, we have c, which is our speed of light in centimeters per second. But then we have this I, and that's the moment of inertia. And what is the moment of inertia? It's mr squared. So that's very, very similar to what we have in the particle in a box, ml squared. So what you learned in the particle in a box is applicable to rotational spectroscopy for sure. As the bonds of the molecule, that's what R is, as the bonds of the molecule get bigger, then the energy levels crush down and they get closer and closer together. Same with the mass as the mass gets larger. So we have a new quantum number. Here's our energy level equation. So every spectroscopy has an energy level equation, and the quantum number is J in this case. So what are the ones that we've had so far? We've had 1dPb. E of n is n squared h squared over 8ml squared. We have the vibration or harmonic oscillator energy with respect to V is the quantum number, is equal to hc nu times V plus 1/2. So very simple equations. These are all the energy equations. So if you were to draw an energy level diagram, you put in the quantum numbers, and these are the energies of the energy levels. Okay, so B is the rotational constant, and I is the moment of inertia. And so as something's spinning around, we can determine, how much mass is off of the axis that's spinning. Okay, that's why I was spinning so slowly. A lot of mass. Okay. And so it's also, these R's are not necessarily the bond lengths. So this right here, this R, is this distance right here. You see how that's not the bond length? That's the distance from the rotating axis. So if I'm spinning around this axis here, this is the R and this is the M. Okay. And so when water's spinning around this axis, there's two M's and two R's. Okay. And the oxygen's right on the axis of rotation, and so it's not adding anything to the moment of inertia. So this has a really, really small moment of inertia because it's just the hydrogen spinning around. If we were to rotate around this axis here, which goes through the center of mass, the center of mass is not exactly where the oxygen is. It's pulled down just a little bit because of the hydrogens. And so the oxygen is moving around this much, and the hydrogens are moving around this much. Does that make sense to everybody? The hydrogens are moving a lot, and the oxygen's barely moving. But that's going to be a different R because we got a different axis of rotation. Okay. Now we're talking about the molecule spinning in space. So these are not, even though this one's labeled C2, like this is not a symmetry axis, but it is an axis that it can rotate around. So we're just dealing around the Cartesian axis, Rx, Ry, and Rz. So I might just call this one Z and erase that C2 because it's not really, we're not doing symmetry on this. So that's Z, X comes out of the paper, and this is Y, the Y axis. For ethane, we have lots of different atoms. And so we have, this is a weird one. This is, atoms A, like these might be H's, and these might be deuteriums. And so here we have 3 times the 3 A masses times their distances from the axis, and here's 3 times the deuterium masses times their distances from the axis, and so on. So the moments of inertia get more complicated with the bigger the molecule. So let's think about how these energies relate to each other. So think about how light an electron is. It's 1,000th of the mass of a proton. So it's really, really light. And so the energy level differences in the electron spectrum are huge because what's in the denominator, that tiny little mass of an electron. It's huge differences in energy levels. So our electronic spacing is in the UV visible spectroscopy range, really short wavelengths and so on. If we zoom in down here at the bottom, we get to the vibrational levels. So these are just the bonding of the molecules. So we have bigger atoms, what do I want to say? Bigger atoms, but we still have pretty small boxes. The atoms are vibrating past each other, so it's a tiny little box. Okay. So it's still, it's much, much smaller in energy than electronic, but it's much, much larger when compared to rotational. So if we zoom in on the ground state of the vibrational manifold and zoom in on that, then we start to see the rotational energy levels. And why is that? Well, because the whole molecule is rotating now. So we got a huge box, if you will. The size of the system is larger than a vibration or a single bend of things. So think of me, my finger's moving, that's the box for my finger movement. And that can move a lot faster than my whole body, which is a bigger box, and more mass is moving too. Here, just my finger mass is moving. Here, my whole body's mass is moving. Okay, so the bigger the mass, the smaller the energy levels. Now, the infrared, the mid-infrared, it gives us our vibrational spectra, the peaks and so on in vibration. And then the microwave region is what we see with rotation. So that's why I say it's really not that relevant to us in class because we don't have a microwave spectrometer. We do have an infrared spectrometer. And so these rotational energy levels are in the ground state. They're also in the excited states. And so when we do a vibrational measurement of a gas phase molecule, we can see the rotational structure from the ground state to the excited state. So we can combine rotation and vibration, and that's the next lecture. But today we're just focused on rotation. So light must interact with a rotating molecule. We're not talking about vibrations. We're just talking about the molecule spinning in space. So a molecule must possess a dipole moment for it to directly interact with one photon of light. So this is something that you must identify in a molecule if you're going to do rotational spectroscopy in the microwave. So we'll talk about which molecules have dipole moments in a minute. And then the selection rules are plus or minus 1. So we don't have any overtones or anything like that. So we don't have a 0 to 2. No. Okay. And we don't have a 0 to 3. No. Okay, so just plus or minus 1 in J. Now, up to this point, we've always done the selection rules based upon the symmetry of the wave functions. And it always kind of surprised me when we got to this. Actually, it didn't surprise me at the time. I was an undergraduate, and I didn't have a view of the whole course, right? But I did notice when I started teaching physical chemistry that We use the wave functions to describe the selection rules, but when we get to rotation, we throw the wave function out and we talk about angular momentum. When have we talked about angular momentum in this course? We haven't. But today we introduce it to discuss the rotational selection rules. And then this is the energy transition equation. So if we take the J plus 1 energies and subtract the J energies, we get the transition energy equation. And we'll make a whole lot out of this 2B business right here. So we'll get to that in a second. But let's look at the selection rules. Why delta J is plus or minus 1? Well, light has 1 unit of angular momentum. So you can think of light, when you know what light is, electromagnetic radiation. So it's an electric field that's oscillating like this, and it's also a magnetic field that's oscillating like this. And they're 90 degrees out of phase, so that when the electric field is at 0, the magnetic field is, say, north. Let's see, this is east, so that's north. Yeah, it works out. So magnetic field is north. And then the electric field goes negative, and then the magnetic field goes south. And you see the rotation? It's plus, north, minus, south. Plus, north, minus, south. Plus, north, minus, south. Okay. My cheerleader. Come on. Right? So it's rotating with 1 unit of angular momentum. Now you could also sort of talk about the circular rotation. So like the polarizability could circle with the plus and minus electric field circling like this. And it could go clockwise or counterclockwise. So it could have 1 unit in a positive direction as we do like the right-hand rule, or in the opposite direction as we do the right-hand rule. So you can think of it either as light having circular polarization, still 1 unit of angular momentum, or the electromagnetic field. So light rotates is another way to say that, with 1 unit of angular momentum. So therefore that unit can be added to a molecule. So a molecule is already spinning and it absorbs light and it gets a kick of 1 unit. Or if the molecule is spinning this way and light's going this way, it can go minus 1 on J. It can slow it down by 1 unit. Okay. So Raman involves 2 photons. So what do you think delta J is for Raman, if we're using angular momentum? Yeah, it could be 2 kicks, right? Molecule spinning and light goes bing, bing. It hits it twice, and so it spins twice as fast. Or it slows down too. It could be going in the opposite direction, or light could cancel. So delta J equals 0 is a possibility too. So these are your little photons coming in. You've got like a kick in one direction to make it spin faster, or they cancel, or they go the other way. And so we get delta J is plus 2, 0, or minus 2 for Raman. And that's pure rotational Raman. But I wasn't happy with this, because we haven't talked about angular momentum at all in this course, and then all of a sudden we pull it out of our hat. Look, angular momentum explains the selection rules. So I had a student. She's my student that I wrote the book with. We started looking at particle on a ring spectroscopic selection rules determined by group theory, not by angular momentum, just to see if it could be done. And it could, and we put it in our thesis, and that's what we put in the book, chapter 9. So this paper has been modified a little bit and then put in our book, chapter 9, using the symmetry argument, and we get the same selection rules out. So that was super exciting. As you can see, she's jumping. Okay. So the transition frequencies are separated by 2 times that rotational constant. So here's a spectrum. So we have the energy level diagram at the top, and you see the unequal spacing of energy levels because it goes up as J squared, so they get higher and higher. And if we take the differences, you see the red lines there, those are all differences in the energy levels. That's where your peaks are going to be, those differences. So this is what our spectrum looks like, our rotational spectrum. So lots of lines that are all separated by twice the rotational constant. So that's what you're going to see in your lab, only it will be on top of a vibrational transition, but you'll see individual rotational lines, so you'll see something very similar to that. So this spectrum gives a whole bunch of measurements of the rotational constant. So we could take the difference between those peaks and calculate B very easily. So this gives a really good average and a really good standard deviation on B. And so we can use that to get bond lengths and angles. So we're going to just do a diatomic, so we won't have any angles. So we'll just have the bond length. So you're going to do carbon monoxide, and you'll see the rotational structure, and you'll assign all of the frequencies of those peaks, and you'll pull B out of that, and then you'll solve for the bond length and the masses. When you have the isotopic masses, and you'll solve for the bond length. Now that's easy for a diatomic. It's way more complicated for a bigger molecule. So we won't do any bigger molecules, but this could be done. Now, for water it works out just fine because we have three rotational constants: Rx, Ry, and Rz. So we have three equations, and we have three unknowns. We have the two bond lengths of the OH, and we have the angle between them. So that's a perfect situation. We have three rotational constants, we have three bond lengths. We could do three equations and three unknowns and get really good statistics on all of those. But look at this molecule. We have 1, 2, 3 different kinds of bond lengths on the top. So 4, 5, 6, 7. So we have 7 bond lengths, and we got a whole bunch of angles. 1, 2, 3, 4, 5, 6, 7, 8. 8 different angles. Okay. And so this molecule may not have enough equations because even though it has what did I say? How many bond lengths? 7, 8, 7 bond lengths and 8 angles. We still only have 3 rotational constants because we only have Rx, Ry, and Rz. So we have 3 equations and 15 unknowns. That's a problem. Mathematically, we can't solve for all those bond lengths and angles. But symmetry does help because let's say this is a carbon and this is a hydrogen and a hydrogen and a hydrogen. All 3 of those bond lengths are equal. So we've reduced those 3 down to 1. And it's a methyl group. There's no reason why these 3 angles wouldn't be 120. So we know that angle. So we just really need the umbrella angle. So we've got 1 bond length on the top. We've got this angle right here. We've got this bond length between the carbon-carbon. And if these were deuteriums, okay, then we have we have 1 bond length on the bottom and 1 angle here. So we've reduced it to 1 here, 1, 2, 3, 4, 5. So we still can't really do it. But isotopic substitution helps because really the carbon hydrogen and carbon deuterium bond length, what would make those different? What makes the bond length in a molecule? You probably never thought about that. Why is a CH bond different than a carbon chloride bond? The polarity comes from something. What causes the polarity? What's that? The nucleus and the electrons. What's in the nucleus that causes the charges? Protons. So if I add a neutron, does that change the charges? No. So carbon deuterium bond lengths and carbon hydrogen bond lengths are the same length. The only difference is the mass. So that's really cool. So isotopic substitution doesn't change your bond lengths and angles because it doesn't change the charges. So that's really neat. So we can take these molecules and do all carbon, and we could do some all deuterium, and then we could mix it all up, and we could solve for the structure of these small molecules using rotational spectroscopy. The masses change the rotational constants. So putting a deuterium on there, now I've got 3 more equations. I've got 3 more rotational constants. Putting a different number of deuteriums on there, I've got 3 more and 3 more and 3 more. So isotopic substitution is the way they did this back in the day for rotational spectroscopy to solve the bond lengths and angles of all of these small molecules. So that's just kind of neat. We're not going to do that because it's really complicated, but it's neat. Okay, but that is a fact that you should take home in your head, that changing the isotopes doesn't change the bond lengths. Okay, it just changes the masses. Now we talked about Raman being a 2-photon process. When we do pure rotational Raman scattering, this is what we see. So we see the Rayleigh and the Raman, Stokes and anti-Stokes shifts. Now these rotational energy levels are really close together, so at room temperature we have a lot of excited rotational states. So we see both the Stokes and anti-Stokes shifts. So this is the Rayleigh line. So that's the laser that you're hitting it with, and that's the Rayleigh scattering. And then we have this red shifted Stokes lines, and we have the blue shifted anti-Stokes lines. So let me just go back up here to the energy level diagram. You see the red shifted Stokes lines are when the photon comes in and leaves with less energy. Therefore, the molecule is in a more excited state. Okay. And then the anti-Stokes, the green photon comes in, it leaves with more energy, and so now we're at a lower state. So we've gone down in energy. And then the Rayleigh, there's been no change. It's elastic. So when we interact with the Raman situation, we're interacting with the electron cloud and how it changes, the polarizability of that electron cloud. And so no dipole is needed. So that's really helpful. In fact, we wouldn't be alive if absorption, if molecules could have a delta J of like 0 or 2 or whatever for like, let me think about this. If molecules did not need a permanent dipole moment to absorb the infrared or microwave light, we wouldn't be alive. Why? Why is that? What's everything? Yeah. I'm specifically thinking about our atmosphere. What's in our atmosphere? What's mostly it? What is it mostly? Nitrogen and what's the other 20%? Oxygen, yeah. So 80% nitrogen, 20% oxygen, and about 1% or less, well, about a half of a percent of CO2. So those three are symmetric molecules with no dipole moment. So microwave energy from our planet can leave the planet's surface and go through the atmosphere and escape. Otherwise, we would overheat. That's the greenhouse effect. Water traps that heat. CO2 in its bending mode traps that heat. That's why it's a greenhouse gas. But if the symmetric stretch of CO2 or just the molecule's rotation around the X and Y axis could absorb microwave light, our oceans would have boiled off long ago and we wouldn't have any life on our planet. It would have just been super heated up. Yeah. So, yay. But now, Raman effect, though, can interact with nitrogen and oxygen. No dipole is needed. So, some of the photons that hit the nitrogen and oxygen in our atmosphere will Raman scatter. But we're lucky that it's just like a 1 in a million chance that happens. So very few photons are bouncing around from the Raman effect, but they can happen. Okay, for rotation. So let's look at the selection rules. If we put those in to the transition equation, the Rayleigh line is just the frequency of the laser. The Stokes line, if you'll notice here, we end up with 4B in front. So like the distance between these lines right here is 4B right here, this difference. So every one of these differences is 4B. And remember, B has the bond length and the mass in it, so that's that spacing. And then if we look at the anti-Stokes line, we see it's positive, it goes to higher wave number, and again it's 4B spacing. Now, we don't see a lot of this because most of our lasers have a really wide spectral line width. So you have to have a really high resolution, super narrow line width laser to do pure rotational Raman. So these are the transition equations for the so this is the algebra related to the transition equation. So this is how you do this. And this has been on the homework a couple of times. So let's just go through it again. Anytime I want to look at the absorption transition equation for J plus 1 or any kind of change, notice we have the energy equation. We have the energy equation with respect to J, and then we want to add J plus 1 in there and take the difference. Right? So we want to know the difference between all of the energy levels that go from J plus 1 down to J. So wherever there's a J in the energy level equation, we put a J plus 1. And so that's where this J plus 1 came from, here. And that's where this J plus 2 came from. See, it was J plus 1 over here, and we added j plus 1 in for j, and now it becomes j plus 2. Okay, is everybody following the problem setup? Now, once you've set up the problem, it's just algebra from there. So we just pull b out front, okay? We multiply j through, and then we pull b out front, and then we work through all of the different things. So we have a b times j squared minus a b times j squared. We have a 3b times j, and we have minus 1b times j, so that reduces that to 2. And then we have a 2b, so we can pull that 2 out front. And so this becomes 2b times j plus 1. So these pieces right here are simplified to that right there. And now I've put b in there just to remind you that for a diatomic, this is what we've got. So this is for a diatomic, and you see that reduced mass, and you see the bond length. So that's our structural information is in B. So that's why I keep making a big deal out of where is B in these equations. So if you can solve for B, then you've got an equation and you've got the mass and you've got the bond length. Okay, let's do it for, I think we do one for Raman too. So here's the Stokes transition equation for Raman. So now instead of j plus 1, we've got j plus 2, and we're taking the difference between that and j. So we have j plus 2 times j plus 2 plus 1, okay, and then we subtract the energy equation with respect to j. So we multiply the j's through, then we do the algebra, we cancel out all the things that can be canceled, simplify it. So this j squared terms are gone. We have 5bj minus bj, so we end up with 4. So that's where the 4b comes from. And then we have 4 and 6. So the way this is typically done is we want a single j right here. So we pull the 4 out front. And how do we get 4 out of 6? Right? Well, we could double it and divide by 2. So we pull the 4 out and we end up with 3 halves over here. So this is again if we know what experiment we're doing, the Raman has 4b in its spectrum between its lines. So if we assign all of these lines, then the difference in wave numbers is 4 times that rotational constant. Okay, so let's do a Kahoot. You gotta be kidding. Stupid internet. I put a nastygram into IT to tell them to fix the Wi-Fi in here. They haven't gotten back to me. So I'll just run this through my phone. Come on. Wake up. Oh, it should be working. There it is. Okay, we're connected. Let's try it again. I can see that. Okay, good. Let's turn on display capture and close window capture. Good. Okay, great. And this is how you find my Kahoots. I don't know if y'all know this, but you can go to kahoot.com or create.kahoot.it, and you can search for chem_prof, and you'll see all of my different Kahoots. So here they all are, and you'll see your class number 4448. You can filter the list, and you can see them. They're close, like the L, the lecture number is close. Sometimes they slip forward and backwards, and so this might be from a previous year, and you say, well, this is lecture 16, but last year was 15 or something like that. So here we are, rotational spectroscopy. So we're gonna practice with this one. Okay, we're good. Running this through my phone. So let's see. That's why I finally bought full data. You know, but the pancake head, I like the pancake head, you know. Let's see again. 10, 30. Okay, it's been at 25 for a while. Is there anybody else still trying to get in? Okay, seeing none, we'll go ahead. Are you doing it or no? Okay, let's go. You can probably still join. There's the code at the bottom. If a molecule lacks this, it will not have a direct absorption rotational spectrum. Oh, good. Of course, you could be fast and wrong, but it's always nice to see. Oh, almost a perfect score. Yes, net dipole moment. Okay, what does it mean by net dipole moment? What? Yeah, the whole molecule. So like ammonia. Ammonia, each little bond is polar, okay? And it has a net dipole moment. So the negative nitrogen with the lone pairs is negative, and the three hydrogens are down at the bottom. Okay, now let's do methane. So each CH bond is slightly polar. So each bond has a dipole moment, but the molecule is a net zero, so not a net dipole moment. So with ammonia, we don't have a net dipole moment, but each bond has a dipole moment. So that's why we make sure that we understand it's a net dipole moment. What about BH3? It's like NH3, but look where boron is. Nitrogen, boron. Just looking at those two atoms, you can see that boron has two fewer electrons. So it's lost 2 electrons relative to nitrogen. So NH3 has those non-bonded electrons up on top. If we take them away, what happens to the hydrogens? They're not repelled by that electron domain anymore. So they go planar. They want to get as far away as possible. So BH3 is trigonal planar. NH3 is a trigonal pyramid. Okay, so trigonal pyramid, net dipole moment. BH3, trigonal planar, no net dipole moment. Okay, that's good. All right, fast thumbs. Good job, baby. Which of these molecules will have a direct absorption rotational spectrum? It's not on your phone? Oh, okay. Oh, okay. It's just spinning. It's the Wi-Fi, I bet, because I don't know. My computer it dropped the connection. I was probably going to wait because yeah. Okay. Which will have, yes, good job, water. So here we just talked about methane. It doesn't have a dipole moment, so it's not going to have a direct absorption rotational spectrum. Okay. The CO2 doesn't have a net dipole moment because it's linear. Even though the carbon-oxygen bonds are polar, they're 180 degrees away from each other, so they would cancel. It has that bending mode, and so when it's bending, a dipole moment develops, okay? but that's a row vibrational transition. The rotational will show up on the vibration, but it won't exist by itself in the microwave region. Which of these molecules will have a direct absorption rotational spectrum? You have to sort of put your organic brain on and learn or like remember what these molecules are. There might even be a hint on the screen. Do y'all know what the hint is? When I learned that that was a good organic solvent as a kid, I started using my mom's fingernail polish remover to like dissolve everything in the house. Is this soluble in acetone? Blah, blah, blah. Yeah, it dissolves a lot. Yeah, so acetone. So ethane again, you've got the the two CH3s. It's a very symmetric molecule, so the dipole moment is canceled out. And acetylene is a linear molecule, so even though you have some polar CHs, they cancel out. There's no net dipole. Oh, little flame, drop in the flame here. What are the rotational selection rules for absorption and emission? This is a two-level question here, and the answers here. It's fun as a professor to kind of come up with the wrong answers and to teach something through the wrong answers too. Oh, so close to a perfect score. Okay, so whenever you're dealing with selection rules, it's a change in the quantum numbers. So we're looking at quantum numbers, so that just restricts it to the bottom row, and then you got to figure out which one is which. So this is direct absorption and emission, so that's just the delta J plus or minus 1. This is the spacing between those peaks. The 2B and 4B is the spacing between the peaks, not the selection rules. Okay. Next question. What do you think it's going to be? What's the spacing between the rotational Raman lines? I'm going to get my camera ready because y'all are going to get a perfect score on this one. Do video. You're killing me. I jinxed you. We just did the spacing. Yeah, I was thinking the selection rules. Yeah, I probably would have got it wrong too. No, because I was going fast in my head. No, the spacing between the rotational Raman lines is 4B, right? Because it's plus or minus 2 delta J, and so then you have twice the spacing as you would have in the infrared, which is plus or minus 1J. So the infrared, or sorry, the microwave region is plus or minus 2B, no, plus or minus 1J, and that gives a 2B spacing. Boy, I said that so terribly. Um, Man, that's a 50-50. Wish I could play that question again. Yeah, spacing. And when we're talking about spacing between the lines, lines go with what? Lines go with the spectrum. You have a spectrum, the horizontal axis. Those absorption lines or emission lines are the horizontal positions of those lines. The spacing between those lines in the spectrum in the direct absorption, the spacing is 1 delta J, and it's also 2B. So it's 2B. And then the Raman, which we have a jump of 2 delta J's, 2 J levels, then the spacing in the Raman spectrum is 4B, so it's even further apart. So the lines are in the spectrum. We solve for the y-axis intensities using the transition dipole moment integrals, okay? But it was the transition equation which gives us the location of the lines on the horizontal axis of the spectrum. Okay, let's see. I'm the same kind of person who at the end of Mario Kart likes to watch the little celebration at the end. My wife's like, skip this, let's play again. But no, I like to see the little thing. Yay, pumpkin head. Good job, Sarah. We got 2 pumpkin heads in the top 3. And then the ice cream down here. Good job. All right, we're done a little early. Sue me.